IK elbow locker. In this episode I want to have a look at adding an IK elbow locker to the arm rig that we have created. A IK elbow locker is an extra control that you can enable in such a way that the elbow of the arm 100% blends to that position and stays at that position, which can be handy when you're animating elbows on a table or elbows on knees, for example, when you want your elbow to be fixed in place and allow for some stretching of the upper and lower arm to accommodate this fixed position. So the shoulder or clavicle can still move and stretch the upper arm a little bit while the elbow stays locked in place. So let's have a look at how to set this up. First off, we need an extra control in our setup. So I already created the control shape. If you would use a control which is not a rotation control for the orientation of the IK, for example, if we have now a control where the rotation generates a vector which is used for the IK solver. If you were to use let's say for example an object like this where the elbow points to, so the vector is generated by subtracting the position of the elbow midpoint or the start of the shoulder minus this position which generates a vector, then you could say, alright, I can reuse this object and allow this object to be the locker object. So you have the locker object and the elbow poleVector object in one control. That's a personal preference. The reason that I do not like this and I want to separate this is, for example, the elbow, you will probably have this in a specific space when animating, for example in the chest space or in the main space, and the elbow locker would probably be most of the times in a different space, so in world or in the leg space, for example, or knee. And then if you wanted to enable the locker control, you had to switch spaces as well and then set stepped keyframes to switch the space without changing the positions. So that makes it a kind of bit messy, and I think it's less user-friendly. So that's why I want to keep this as a separate control instead of combining it into one. So first let's add this control to our setup. So we'll reset the position, and then we're going to need an extra guide for this. So let's look at our arm guides and duplicate one of the guides and call this elbow locker guide, and then let's reset this rotation and place the elbow locker, well, for starters, let's put it in the same position as the elbow control, like so. And then we're going to add it to our control setup tab. So let's add the guide and as well the control, and put the control in the controls group. And then we can remove the shapes from the node editor. Alright, and now we are going to do the same thing as we did with the other controls, and we're going to set up the space switches right away because it is kind of the same process as setting up the control, and we want to have the ability to set the control to different spaces in the rig as well. So first off, let's create the main space, which if we look at the other controls, let's see where we were, was the clavicle space was the main space or the default space, if you want, before the parent matrix node that we used for space switching. So let's create a multi-matrix node, and then we input the guide world matrix into the first port of the multi-matrix node, and then we're going to take the inversion multi-matrix of the default space, so the clavicle space, so that would be the clavicle input guide. So the clavicle input guide, or the clavicle guide input inverse world matrix. So now we have the offset, parent offset or buffer matrix, which brings us from the parent guide, which is the clavicle guide, to the position of the elbow locker guide. So let's call this the elbow locker parent offset matrix. Or maybe have guide in there. And then we are going to create the world matrix for this. So we do another world matrix. And then we are going to multiply the offset, parent offset or buffer matrix with the world matrix of the parent, in this case the control output of the clavicle control, which we have linked to the clavicle input node. So we take the offset parent matrix plug of the clavicle input node, and then we plug it into here, and now we have created the world matrix which moves along with the parent control. So if we take our control, and if we would now connect the output of the world matrix into the offset parent matrix, you will see that the control is nicely at the correct position, and if we were to move the clavicle control, it would nicely move along with the control or with the clavicle output matrix. So now to use the space switching, we're going to use the parent matrix node, so let's add that in between. So we reroute the plugs to put it in between. And then we can set this to be the control clavicle space world matrix. I believe this is the way that we named the others as well. Clavicle space world matrix, yes. And then this would be the switched or the final world matrix of the control. Like so. So what we're going to do for this one, we're going to add two spaces. So we're going to add the main control and the world space to both of these. So most of the time you will probably have the control in the main control or in the world space. And the clavicle space that we are using now might not be a very useful one for the elbow locker. Having said that, I think that we should skip the clavicle space and replace it with the hip space, because we're probably never going to use this in the clavicle space nor in the chest space. Hip space might be a space that we use. So let's switch this to use the hip, main and world space. So rename this one to be the hip space. And then this as well should be hip space parent offset matrix. And then we're going to change this plug to not use the world inversion matrix of the clavicle, but of the hip. Maya does not allow for this. So let's open this one up. Hip guide, world inversion matrix. Take this plug and plug it into the second port of the hip space parent offset matrix. So now we're calculating the offset or buffer matrix from the hip guide instead of the clavicle output. So, and then we need to reroute this plug as well. So we're not taking the clavicle offset parent matrix, but we're going to take the offset parent matrix of the hip, which is right here. So now when we use the clavicle control, you will see that the control stays in place. If we use the chest control, it will stay in place, but if we use the hip control, it moves along with the hip control. So now that is changed, let's add the spaces for the main control and for the world space. So let's create another world matrix node to create the offset or buffer matrix. So again, input the world matrix of the elbow locker guide as the first plug. And then in the second, we're going to plug the inverse world matrix of the space guide parent. So in this case, the hip. So let's look at the hip inputs, which are, sorry, we're going to use the main. The hip we already did, so it's going to be the main. So the main control, the main input, and we're going to take the main guide inputs, world inverse matrix. So let's plug that into the second port. So now we have created the main space offset matrix. Like so. And then to add the space to the parent matrix node, we could plug the offset matrix into the offset matrix, and then we can use the target matrix. We plug it into the output of the parent, in this case the main. So the main control, we take the input node for the main control, which is connected to the output of the root module's main control. So we take the offset parent matrix plug, and then we connect it to the target matrix of the parent matrix node. So now when we enable the space, the hip control does not influence the elbow locker control anymore. It's now completely locked to the main control, like so. And then we needed to add the world space as well. And if you remember correctly, we can just use the world space matrix of the guide, because basically this is the offset matrix, which brings us to here from the origin of the world. So this is already the offset matrix, and the driver matrix will always be the identity matrix, or the target matrix, because the world space does not change. It's always at the origin of the scene. So let's plug the world matrix of the elbow locker guide into the offset matrix. And now we have our three spaces, the hip, the main, and the world space. So for this control, we have to use a different attribute for space switching, because we're not going to use the same space as the arm, because we want to be able to use different spaces. So we're going to add the space switch to the control. This will introduce a small cycle loop, because we're going to use an output of this control and feed it back into the parent matrix node. But because this is only 2 nodes, and we're going to use some equal nodes as well, so it's a relative small cycle cluster, which is not very influential in the evaluation. You could as well add the space switching to the settings control, like we did the space switch for the arm, but it's then you have to select another control. So it's for this control we're going to this. It doesn't really matter where you add it. Adding it on the settings control will be slightly faster, because you don't introduce the cycle loop in the node editor, which is a benign cycle loop, as said, because we're not influencing the same attribute by something that's influenced by an input attribute. So it's only evaluating the selected nodes in the cycle loop in a DG evaluation mode. But in the rig, probably there's a lot of stuff that can be evaluated in parallel besides that, so the impact is small. Okay, so let's add the switch attribute. So okay, add attribute, we're going to use an enum again, and we're going to call this space again, and then the first input will be the hip, and then the second will be main, and then the third would be world. So let's add this one, like so, and then we are going to again use the equal nodes to test if the current space is active. So we take the space attribute and plug it into the input 1 of the equals node, and then we say if it is equal to 1, then we need to activate the second space, in this case the main control space. So we take the output and we plug it into the enable target for the first target, and this is the hip space, the main space. So let's call this the main space enable node, and then let's duplicate this one. Okay, Maya zooms out, and let's call this world space enable. And let's take the same space switch attribute, plug it into the input 1, set the input 2 to be 2, and if this one is true, then the world space target needs to be enabled. So we plug it in here. So with this we have created this little cycle cluster in the evaluation graph, which will be evaluated in DG. So when one of these nodes has to be evaluated, which is probably going to be this control which is triggering it, then Maya knows that these nodes are all in the cycle cluster. So it takes all these nodes, evaluates them in DG, and once all the attributes of these nodes and all the data has been set to clear or not dirty, then the other nodes that are dependent. So now that we have the control set up, let's lock and hide these attributes as well, because we're only going to use the position of this control. And now let's see if we are in the hip space and we rotate the hip, you will see that it moves along with it. And if we then change it to be a main space and we rotate the hip, it stays locked and it moves along with the main control. And if we switch it to be a world space, then even the main control does not influence the control position. So that's the control part set up correctly. Let's switch this back to hip. So the next thing we need to do is to have the control be able to take over the poleVector task of the IK solver. So now we're using the IK elbow control. So when we enable the elbow locker, this node has to generate the poleVector for the IK solver. So first let's add an enable attribute for this. So add attribute, make it a boolean, we call this lock, and then OK. So for now put it to on. If we look at the IK solver, I have it still open in the tab. This part is the soft IK, so all these nodes, and then we start here with the length of our IK segments, and then the IK solver part, and the IK elbow control is used here to generate the matrix where the IK solver, which is happening in local space, is transformed to the world position and orientation. And we're using the elbow IK control to orient a matrix that starts at the arm upper start position, aims to the hand, and then orients that plane according to the IK control, elbow IK control. So what we now need to do is to be able to switch the secondary input of the aim constraint. We want to be able to switch this part to use the locker. And now we are using a matrix, and we're setting it to be in the alignment mode. So we have to switch, because when we are using the elbow locker control, which is a position, so you could use an aim mode. But if we generate another vector from this IK locker control, then we can use it as well in the alignment mode. But now we're using the Y vector to be multiplied with the matrix of the IK elbow control. So we have to switch this to not use a matrix, but just use a vector. So let's set that up, and first maybe generate the vector for this control as well, the vector that we need to align the arm. So to generate the vector, we can just simply take the world position of the locker control and subtract it, subtract the start position of the arm, the start position, world start position of it, and then we get a vector that points from the start position of the arm towards the locker control. So if we look at the inputs of this IK solver, we have the base matrix that we use as a starting point. So if we create a temporary locator and we take the output of the upper FK control clavicle space world matrix, we renamed this when we added these spaces, and if we plug that into the offset parent matrix, we see that this is the control that we're using. So the name for this node is kind of elusive, so maybe let's rename it, because we're using it for the FK upper control, but we are as well using it downstream here for the elbow IK control as its basis orientation matrix. So maybe we should just call this upper world matrix, or upper base world matrix maybe, and then we can call this upper base parent offset matrix, and which feeds both into the FK and the IK control rig. So now, and this reads more clearly. So we have the upper base world matrix, which is this matrix here. And now we can take the position of this matrix by creating a translation from matrix. And if we plug in this matrix, we get the world position for this matrix. Now we have to do the same thing for this control. So let's add it to our graph here. And the shape we can remove from the graph. And then let's take this position node and call it upper base, let's see, world position. And then this control, let's also create a translation from matrix and plug in its world matrix. And then let's call this elbow IK control world position. Now we have the two world positions, and now we can use a plus min average node and set it to subtract. And then in the input 3D part, we can firstly plug in the elbow IK control, because when you subtract two vectors, you can remember the first one you plug in, that's the position where the vector points towards. So if we take the IK control, the elbow lock IK control position as the first, and the arm start as the second, then it will point from here to there. And then we take the upper base world position, plug it into the second, and now we have the vector. So let's call this maybe the elbow lock IK poleVector. And let's take this poleVector all the way to here, maybe these nodes as well, because we're not using them for anything else just yet. Like so. So now we have the vector, the poleVector for the elbow locker control, and now we need to generate a vector for the IK control. So we can do this by creating a matrix, it's called multiply vector by matrix. So we're basically going to do what the A matrix node is doing internally. We're going to create a vector, the Y vector, and multiply it with the world matrix of the elbow IK control. So that's basically happening in this node as well. So we set the vector to be 0, 1, 0, and then we plug in the world matrix into the matrix. And then we can call this the same way, but just without the lock. So it's the elbow IK poleVector. And now we can take the aim control for the aim matrix, And then we can disconnect the matrix because we now have a world space vector that we are going to use. So we disconnect the matrix, and then we have to make sure that the matrix is set to the identity matrix. So we have to reset all the values. So the translation needs to be 0, the rotation needs to be 0, and the scale as well. Now the IK solver flips because we have not set in the correct vector, because the vector now is the world y vector, which is pointing upwards. So this is correct for the settings. And if we now take, for example, the elbow IK poleVector and plug it into the secondary vector, then you see that the arm is back to its normal state. And if we rotate this, it's still working. And if we then switch it for the elbow lock IK poleVector, then the arm stays in the same position because the control is aligned with the elbow. And if we now move this, then you'll see that the elbow now follows the locker control. So we have to be able to switch between these two values, and we can do that by using a blend colors node. This creates a blend between two vectors. And the funny thing about this node is when the blender is set to 0, it takes 0% of the first. So it is 100% set to the second color. This is kind of counterintuitive because most nodes blend to the first input when it's set to 0 and to the second input when it's set to 1. But for this blend colors node, it's actually reversed, so that's something to keep in mind. Basically, it's doing the blender multiplied by the first, and then the one minus the blender multiplied by the second color. So you can see if I set this to 1, then the red color is 100. So if we look at the output for this node, you can see that the output is 100. So it's the red color, and if we set it to 0, then it will be 0, 1, 0, because that's the blue color. So, oh sorry, 001, because it's RGB, it's the last one. So you can see how the switching works. So thinking about this, then we are going to not use a Boolean attribute. We want to be able to switch gradually from the IK elbow control to the elbow lock control. So let's switch, let's remove this one and make it a float attribute. So delete attribute and then add attribute. Let's make it a float. So we'll call this lock, and then has a minimum of 0 and a maximum of 1, and press OK. And for now, let's add it here. So we're going to take the lock attribute and plug it into the blender. And when we are setting the lock to 0, we do not want to use the lock. So we are using the elbow IK vector and just saying that when it is 0, it is taking the second input. We need to plug the IK poleVector, the elbow IK poleVector, into the second color. So plug that into there. And then we take the elbow lock IK poleVector, plug it into the first color, and then we take the output and plug it into the secondary target vector. So now, if we have done this correctly, with the lock to be 0, this control does not have any influence, which is correct. And if we then switch to the lock on, you will see that the control has all the influence over the elbow. So that's the poleVector part done. Now all we have to do is make sure that the elbow position, or the joint, is actually at the position of the lock control. So let's leave this in this position, and let's add that. And maybe first rename this node correctly. So let's call this the IK poleVector switch, like so. So the lengths of the IK solver are now calculated by the base length of the arms. Then they are multiplied here somewhere by the manual scale here, where we have added the upper and lower length scalars. So they're first multiplied by those, and then they feed into the scalars for the soft IK, and the output of the length scaled, the upper and lower length scaled, are the lengths that are feeding into the IK solver. So when we are enabling the elbow locker, we want to override the length to be the exact lengths coming from the upper start of the arm to the elbow locker control for the upper arm segment, and the length that's coming from the elbow locker control to the hand control to be the lower segment. And we want to disable the soft IK because we don't want the elbow to move away from this position. So even when the arm is in the soft IK range, we want it to stay locked. So basically what we have to do is just add a switch after these length scaled nodes to switch to the absolute length that flows from the control positions. So let's do that. And remembering that we are creating or solving the IK in local space, where the scale, the global scale of the rig does not exist, because we are adding the scale to the IK solved joint positions in the last step. It's coming from the aim matrix that we set up here. If we, for example, scale the control rig, the main control rig, and we look at the output of the aim matrix, so the second input of this control, this node, you will see that the scale of the main control is already in this matrix. So that's why we, in a episode before, we had to add the no main scale multi-matrices, where we multiplied the world matrices of the hand control and the upper base world matrix with the inverse world matrix of the main control to remove the scale from the calculation of the arm length segments, because otherwise we would have double scaling. So we have to do the same thing for the elbow locker. We have to calculate the position of the unscaled main control. So we're going to do the same. When we take this control, let's move it back to the beginning, and we're going to create another mult matrix to do the same. We're going to take its world matrix, and then we're going to multiply it with the inverse world matrix of the main input. So that way we get a, let's say, create another temporary locator. If we now take the output and plug that into the offset parent matrix, you will see that the locator is still in the unscaled position. If we remove the scale from the main control, not 0, 1, you can see that the positions align, or they should align if the main control would have been on the root position. You can see that because of the offset of the main control, it also has an offset because it's multiplying it with the inverse matrix of this control, basically, which also has the offset incorporated in it. So if we would set this on the origin, you can see they nicely align as well. So if we now scale the main control, you can see that the locator does not scale, and the same goes for the other controls. They would have a, if we create another locator, for example, of the shape, and we take, for example, the upper, so let's rename this as well, because we changed the name. Upper base world matrix, no scale. If we take that output and plug it into the offset parent matrix of this control, you will see that it has the same offset as the main control, or the inversion of the offset of the main control. And if we scale the main control, then the locator stays in its fixed position. So we have the world matrix without the scaling of the main. And now we can use this world matrix to calculate the absolute or the unscaled upper and lower arm segments by using the translations of these matrices. So let's take for the upper arm segment, we have to take the world base world matrix, no main scale. We can plug it into the input matrix. And then we need the elbow locker world matrix as the second. So plug that into the input matrix 2. And this is the upper alarm. So let's call this maybe elbow IK upper length. And then create another distance between node. And then we are going to take the distance between the elbow lock world matrix and the hand IK world matrix, like so. And we call this the lower length. Like so. Okay, and now that we have these, we can use these to down here to switch to for our IK solver. So the upper and the lower, we need to switch between these two, and we need to switch between these two. And because the outputs of this are just a single float, we can use the blend to adders node for this. So blend to adder. We can use the same enable attribute on the lock control to drive the attribute blending. So let's go here and take the lock attribute, the float value, and plug it into the attributes blender. And for this node, it's the other way around compared to the blend colors, because when the attribute blender is set to 0, it will take the first input, and when it's set to 1, it will take the second input. So if we want the value of 1 to be the lock enabled, we need to set the first input to be the length that we calculated before, the upper arm segment length, and then we take the elbow lock up length to be the second input, and then we have to take all the outputs and reroute them into the output, like so. And you can see that the upper segment already has adjusted to the new length. The geometry is not going along. I will look at that in just a minute, but it's just a visual representation. Let's call this the upper elbow lock length switch, like so, and then duplicate this node, and we call this the lower version. And then again, we are going to show all the attributes, and we're going to take the attribute blend attribute from the lock attribute of the elbow lock IK control, plug it into the attribute blender, and then we are going to set the normal length we calculate before as the first input, and then we're going to take the lock length as the second input, and then we're going to reroute all the output connections to the output plug, like so. And now you can see that the elbow joint is at the correct position, and if we move the elbow locker you can see that the arm length adjusts so that it's always 100% locked to the position. So let's now fix the geometry lengths to get a more visually pleasing representation. So let's have a look where we added those. Not here, and not here as well. Let's just graph them. We are getting the scale from the upper length scaled, which is this node. So we have to take this and add it, and we have to take the output and plug it into the scale X like so, and the same for the upper arm or lower arm segment. The input is coming from the lower length scaled, which we have now routed to this node. Add that one, and then take the output of this like so. All right. So now we have enabled the length for the proxy geometry as well. So the elbow locker now functions like so, and if we switch, it will nicely blend to the other elbow control and the lengths that are calculated from the base length, the manual scale, and the soft IK setup. So now when we have this locked to a hip space, for example, if you wanted to character to have the elbow in the front of the hip, then now if we rotate the upper body, the elbow will stay at the correct position. And if you move your clavicle as well, the upper arm length will adjust to keep the elbow in the correct position. And if we were to change the space to the main space, then now if we change the hip, then the elbow will stay in the same position, and if we move the main control, it moves along. So everything seems to be working. Maybe one more thing that we need to check is that if we are going to scale, everything maintains working, and that seems to be the case as well, even in the non-uniform scaling modus. Alright, let's reset the controls to the default positions and disable the lock and set the space to be the, well, main, doesn't really matter. And there's one more thing that we can add. If, for example, the elbow locker is in the main space and you have animated your character off and you've rotated it somewhere, then it could not be very visually logical where this control belongs to. So what we can do is we can add a visual aid to this control that creates a line that goes from the control to the elbow so that it's clear where the control belongs to. So let's add that now. So if we go to this tab, for example, and we have to create a NURBS curve, we're going to create a simple linear NURBS curve with two CVs, where one CV is on the control and the other CV is on the elbow. So let's create our NURBS curve, and I'm going to create a linear NURBS curve. I'm going to create a curve with two CVs. I'm going to create the CVs at the origin. So two CVs at the origin. So we now have created a NURBS curve with length of 0, where both the CVs are at the origin. And the reason for this is that we're going to drive the CV positions directly. So a lot of people still use clusters to drive curves, but that's really unnecessary because that adds a deformation chain to the geometry of the curve, and we can just drive the controls directly. If you look at the input attributes of the curve shape, you can see control points, and this is where you can add an offset, so to speak, to the curve data that is stored internally. to the nibs curve. So it has a CV position, and if you set the control points, these are basically added to the positions of the CVs. So if we take the, let's say the control, and we have not created or did we create a world position for this? Yes, we did. So let's take this node and add it to our node graph. So we have the output of this is the world position of the control. So if we take the output and plug it into the CV control point 0, you will see that the CV now is at the position of the control, and if we move the control, it nicely follows along. So we can do the same thing for the elbow position. So if you go to the IK solver and see where we calculate the world matrix of the lower arm, so that would be this. So if you create a temporary locator to make sure, if we take the world matrix or the matrix and plug it into the offset parent matrix, you will see that this is the position of the elbow. So, and if we rotate it, you can see it moves along. So this is the position that we're going to set as the other position of the curve. So we can remove the temporary locator and take this node and add it to our panel, and we take another translation from matrix, and we take the matrix, plug it in, and then the output we put into the control points 1 slot, and now you can see we have connected the curve to both ends. And if we now rotate, it will update to the correct position, and the lock control will drive the other position. So let's call this world pos for world position, and we call this one the, let's say, elbow lock IK helper or visualizer. I don't know, create a nice name for this. We move this to the helpers, and then maybe we give this a nice color. Let's do it in here for a change. So by object display, drawing overrides, enable overrides, and maybe make it dark purple. Not so much. Light green maybe. I don't know. We could do as well with a, maybe use the guide color. Like so. Maybe that's more clear. If we hide the guides, you have the line in that color that stands out a little bit more. Alright, so that's how you would create the helper curve. And then as a last addition, you could add as many spaces to this as you would like. You could also, for example, if you have the legs implemented as a module, you could add the output of the knees of the legs as inputs in the arm module, and add the knee as a space to the poleVector or the elbow locker as well. So you can lock the elbows to the knees, for example. If your character sits with its knees resting on the its elbows resting on the knees of a character, you can lock them that way. And you could also maybe write a tool that adds spaces dynamically, or you can just constrain the control as well in any space. So that's how you could use this and set it up. So let's reset all the values, and then we can move on to a new episode.